This is Cosmographia, the Randall Carlson podcast.
We are back, ladies and gentlemen. This is Cosmographia, the Randall Carlson podcast. This is episode 103. And what's the word on the streets, Randall? We're going to keep talking about the sun? Where are we going today?
I thought we'd talk about the sun. I thought we'd talk about some of the influence of the sun on climate. I thought we'd talk about some of the sun being composed of plasma, and what happens when the sun decides to hurl huge bolts of plasma at the Earth.
Yeah, I've seen there's been some auroras pretty far south the last couple of nights. Some amazing stuff.
Yeah. Now, did we talk about the 14,300 year ago event? Have we talked about that in this show?
Yes.
We did, yes.
Last episode.
Yeah, last episode we talked about the Miyake events and how they just found one at 14.3.
And then who pulled up the paper possibly redating meltwater pulse 1A to 14.3?
I haven't seen that one.
Okay, who did that? That might have been on the tour.
Somebody told you about that.
Yeah, I should have taken it.
The last show.
Was on the show.
We had talked about it. Because when we were looking up the Miyake events and that 14.3, I looked up meltwater pulse 1A. And saw that its range was within, like that it basically is a range of when they think it might have happened, and that event is within that range. We talked about that last year.
Okay, and then since then, someone has referenced me a paper that is actually redating meltwater pulse 1A to 14.3.
Okay.
It might have been on our tour we just finished.
You got it.
Interesting stuff, for crying out loud. It shows that there's other vulnerabilities potentially affecting us here on this planet. Well, this is kind of what Robert Schoch's been saying all along, right?
Yes, for sure. He actually commented a little bit on the Miyake event paper.
Oh, did he?
Yeah, for sure. He was saying, like, this is what I've been saying. It's the sun that's been causing these events.
Well,
1 out of 3.
Yeah.
1 out of 3. See, I guess I don't know where his latest thinking on it is. The only thing, I've never disagreed with Robert that the sun plays a critically important role. Where if there is a disagreement, it's that impacts of comets and asteroids and things don't play a critically important role and had no role to play in the younger Dryas.
Yeah, and the fact that they've found roughly one of these events every 1,000 years or so, going all the way back, sort of argues against it causing any particular massive cataclysm at this point, right? Unless maybe it did. I don't know. But if they're fairly frequent, and we don't have other catastrophes every time it happens, then what's the explanation?
If what are fairly frequent?
The Miyake events, the solar outbursts.
Yeah. Okay, the solar outbursts, right.
Yeah.
Well, if there was a solar outburst, of course, correlation is not causation, but if there was a solar outburst at 14.3 and we have a giant meltwater pulse at 14.3, one, I think, could assume that there would be some kind of a connection, and I would assume that it would be unidirectional. I wouldn't assume that the meltwater pulse would cause a solar outburst, a Miyake event. I would think it would have to be the other way around if there was causation. If there's no causation, and it's purely a coincidence.
Or, like you've said several times on the show, that it's both the comet and the solar event, right? In other words, giant part of the comet falls into the sun, causes a massive outburst. Also, the Earth is getting bombarded, so the outburst and the impacts happen in the same period.
Yeah. I think that sounds like a plausible explanation to me.
Yeah, so they are connected, but it isn't necessarily causal.
Right. So we have some very interesting research. We may have covered this already, but it wouldn't, it's valuable and important enough to warrant a revisit. And this was the explosion of sun-grazing comets in the solar atmosphere and solar flares. This appeared in the Universal Heliophysical Processes Proceedings of the International Astronomical Union Symposium number 257 back in 2009. And this is what it says. Explosive evolution of nuclei of sun-grazing comets near the solar surface, which occurs at conditions of intense interaction between the solar atmosphere and falling high-velocity comet nuclei, as well as the relation of the phenomena to the character of solar activity, are analytically considered in this paper. It is found that, due to aerodynamic fragmentation of the falling body in the solar chromosphere and transversal expansion of the fragmented mass under the action of the pressure gradient on the frontal surface, yes, we have covered this, thermalization of the kinetic energy of the body occurs by a sharp stopping of the disk-like hypervelocity fragmented mass near the solar surface within a relatively very thin subphotospheric layer, and has therefore an essentially impulsive and strongly explosive character. The specific energy release in the explosion region in terms of ergs per gram considerably exceeds the evaporation sublimation heat of the body, so that the process is accompanied by the production of a high temperature plasma. The energetics of such an explosive process corresponds to that of very large solar flares for falling bodies having masses equal to the mass of the nucleus of Comet Halley. So right there, what this is telling us is the possibility that a cometary mass roughly equivalent to that of a nucleus of Comet Halley falling into the sun could produce a high temperature plasma explosion.
And Halley's about 10 miles across.
Yes. So what would let's say a cometary mass that's 50 miles across, or, 2 orders of magnitude more massive than Halley? And what if there was a succession of such events, or a series of smaller events clustered falling into the sun? See, that's where I'm thinking that research needs to go in that direction. Now that we know that there are sun grazing and comets and objects that do fall into the sun and apparently produce pretty substantial responses in the chromosphere of the sun.
Yeah, and I guess then another question would be, are these events almost all, like these Miyake events, usually being caused by infalling bodies, or will the sun just make them on occasion as well? Because the interesting thing about the one that happened at 14.3 was it happened during a minimum period.
Mm-hmm.
And you usually think of an enormous solar outburst happening during a maximum period, of maximum solar activity. Like, usually during minimums, you get no sunspots and no corresponding flares and no massive outbursts and CMEs, or very few, right? And they're small. You get the X-class flares during solar maximums.
Mm-hmm.
So,
and what
maybe
length cycle is that? That like 11 years?
Right. Yeah.
So that's pretty tight dating then, if they're gonna say 14.3 is
no, they were calling it a Maunder type minimum, so a long period of very low solar activity. So the minimums would be even smaller and the maximums would be very small too. Right? The 11-year cycle, all of it would be lower energy during a Maunder type minimum.
So let's see, the paper I just read from was in 2009. I have a 2015 paper here. Appeared in the Astrophysical Journal in 2015, entitled Destruction and Observational Signatures of Sun Impacting Comets. And this is by John C. Brown, Robert W. Carlson, no relation that I know of, and Mark P. Toner. Okay. Motivated by recent data on comets in the low corona, we discuss destruction of sun-impacting comets in the dense lower atmosphere. Extending earlier work on planetary impacts to solar conditions, we evaluate the mechanisms and distribution of nuclear mass and energy loss. Sun-impacting comets have energies comparable to magnetic flares. This is released as a localized explosive airburst within a few scale heights of the photosphere. Such airbursts drive flare-like phenomenon, including prompt radiation, hot rising plumes, and photospheric ripples. The observability and diagnostic value, which we discuss in this paper. Isaac in 1981 suggested that sun impactor momentum deposition could generate helioseismic waves and contaminate global helioseismic signals. So you're literally talking about here solar earthquakes. The idea was discussed briefly by Gao in 1994 in the context of possible Jovian seismic waves induced by the Shoemaker-Levy 9 impacts. Let's see. So he concluded that only a very large impactor would be detectable in global helioseismic signals. However, that does not preclude detection with modern hardware and analysis methods of transient sunquake ripples near the sites of lower mass impacts, similar to sunquakes following some magnetic flares. The relationship between flare and sunquake properties proves to be complex, some small flares producing large quake signatures and vice versa. One theoretical issue is that of radiative damping in the dense chromosphere of downward impulses from explosions at higher levels. The lower altitudes, smaller volumes, and faster timescales of cometary airbursts compared to flares, together with their highly directed motion, make them seem more likely to generate stronger helioseismic signatures. So what this so far is suggesting to me is the possibility that there is a relationship between solar activity and the flux of material in the solar environment that could be falling into the sun on a regular basis, sometimes with greater frequency or greater magnitude than at other times. So to me, this kind of opens the possibility of there being a correlation between the influx of cometary masses into the inner solar system and a solar response.
Was that also suggesting that it sounded like it was saying that there's a correlation between seismic activity on Earth and flares? Is that what it was saying, or was it specifically talking about sunquakes?
I think it's talking about sunquakes.
Okay.
Mm-hmm.
Because there is some interesting ideas that large solar outbursts hit the Earth's magnetic field, and that magnetic field transfers a lot of that energy to the inner planet and may result in seismic activity on Earth or volcanic activity as well.
Well, that would seem to me to be logical.
Yeah.
I mean, what I think we're approaching here is an integrative model, where all of these things are part of a system, an interactive system. So we're looking at comets in the Oort cloud. We're looking at comets in the Kuiper disk. We're looking at the placement of the big outer planets. We're looking at the sun. The whole thing is a system. And that every part that something that affects one part of the system can have a ripple effect throughout the entire system. That's why I kind of think we need to be looking at some of these events like the Younger Dryas and perhaps the 14,300 event and so on as events that do encompass the astronomical domain of things on the larger scale and not merely terrestrial. Yeah. And then a lot of the things that you just mentioned, what you brought up, Russ, sort of implies the possibility that there is a terrestrial seismic response to what's happening in the electromagnetic field of the heliosphere.
Yes.
Yes.
Yeah, if the Earth, I mean, it seems to make sense. If the Earth has a magnet, a dynamo somewhere inside of it that's highly magnetic, and it should be responsive to magnetic impulses from the sun, right? And that would, I mean, like anybody who's pushed two magnets toward each other,
yeah,
you know, with the same side, you can see how there's this opposing force. You can feel it, right? And so if the sun puts out a huge magnetic pulse and that hits the Earth, some of that force is going to be transferred to the inner Earth, to whatever is causing the magnetic field.
And the same could also hold true for volcanism.
Yes, right.
So here is a 2002 paper that appeared in the Philosophical Transactions of the Royal Society of London by Louise K. Hara, who is a solar scientist. She says in this paper, I describe two of the most dynamic and highly energetic phenomena in the solar system. The explosive flares that can occur when plasma is confined by magnetic fields. When plasma is confined by magnetic fields and the large-scale ejections of material known as coronal mass ejections. These explosive events are poorly understood and yet occur in a variety of contexts in the universe, ranging from planetary magnetospheres to active galactic nuclei. Understanding why flares and coronal mass ejections occur is a major goal across a wide range of space physics and astrophysics. Although explosive events from the sun have dramatic effects on Earth, flares in other stars, for example, can be vastly more energetic and have an even more profound effect on their environment than that of our own sun. Now, that brings up, an interesting point, is that many of the other sun-like stars that have been observed seem to be much more energetic than our sun. Now, is our sun unique from those? In other words, is there some inherent quality of the sun that makes it less dynamic than the sun-like stars that we're observing? Or is it possible that there is a long-term cyclicity to the sun, and there may be times when it is much, much more dynamic than we've experienced in historical times? I think that's an important question that needs to be considered. So let's see. She goes on here saying this. We are now in the unprecedented position of having access to a number of space observatories dedicated to the sun. And she names the sun. We named these in the past episodes, so I won't repeat them. But again, I will repeat this. These cover a wide wavelength range from white light to gamma rays with both spectroscopy and imaging, and allow huge progress to be made in understanding the processes involved in such large explosions. The high-resolution data showed dramatic and complex explosions of material on all spatial scales of the sun. They have revealed that the sun is constantly changing everywhere on its surface, something that was never imagined before. So this is written in 2002, 10 years after the first IPCC paper was published. in which any role of the sun in terrestrial climate change was dismissed or ignored, which is essentially where we're still at with the climate change scenarios.
They've basically treated it as a constant. Is that?
Yes, the solar constant. And if it's the solar constant, then you can, for all practical purposes, ignore it.
Right.
So, but is that the case? Let's see. So Gerard Bond, he was one of the people who discovered the ice rafting events in the North Atlantic that we've talked about. When you have these disgorges of icebergs, the Heinrich events, where you have large-scale armadas of icebergs loaded with the debris they've accumulated from the continental surface. And when these icebergs float out, they drift south, they melt, and the debris that they're carrying falls to the bottom, right? That's and the signature of that coarser debris marks the Heinrich event. So recently, Bond and others in 1997, this is written in 1999, discovered that periodic ice rafting events in the North Atlantic region were not restricted to the last glacial, but also occurred during the Holocene. They provide evidence that these events were simultaneous with climatic cooling phases. A number of those Holocene climate cooling phases coincide with events studied in detail by others and are most likely of a global nature. As Bond et al. Proposed, the cooling phases seem to be part of a millennial-scale climatic cycle, operating independently of the glacial-interglacial cycle, forced by orbital variations, right? The question remains, however, what is the driving mechanism behind these millennial-scale events? Answering this question is essential for our understanding of climate sensitivity and thus for estimating possible future climate changes. Bond and his colleagues concluded, they suggested that the driving mechanism is to be found inside the atmosphere ocean system. In contrast, we show here that there is mounting evidence suggesting the variation in solar activity is a cause for millennial scale climate change. In Figure 1A, a schematic overview of the various factors in the relation between sun, cosmic rays, and climate is shown. We emphasize the possibly important role of changing solar ultraviolet and solar wind, modulating cosmic ray intensity in the atmosphere. Our ideas are based on existing records and new observations of the cosmogenic isotopes carbon-14 and beryllium-10 in various archives. So this is in 1999. Well, we've come a long way since then. And I think I'll just go through and show you a few papers here. I will do a share screen. Let's see here. Here we go. Screen 3. Okay, this is a small sample that we're looking at here. So here we have a paper from 2001. It is in the journal Science, so it's peer reviewed. Okay, so persistent solar influence on North Atlantic climate during the Holocene. Surface winds and surface ocean hydrography in the subpolar North Atlantic appear to have been influenced by variations in solar output through the entire Holocene. So how about that? Let's go to the next one here. Oh, what do we got here? We got another paper from Science, September 2003, cyclic variation and solar forcing of Holocene climate in the Alaskan subarctic. High-resolution analysis of the lake sediment from southwestern Alaska reveals cyclic variations in climate and ecosystems during the Holocene. These variations occurred with periodicities similar to those of solar activity and appear to be coherent with time series of the cosmogenic nuclides carbon-14 and beryllium-10 as well as North Atlantic drift ice. Even an earlier one, when it was already becoming apparent. 1987, here's influence of solar variability on global sea surface temperatures, which is discussed in this particular paper. Here's one from, what year is this? This is a more recent paper, Length of the Solar Cycle, an indicator of solar activity closely associated with climate. It has recently been suggested that the solar irradiance has varied in phase with the 80 to 90-year period represented by the envelope of the 11-year sunspot cycle, and that this variation is causing a significant part of the changes in the global temperature. So that has been criticized. However, new evidence supports it. This record closely matches the long-term variations of the Northern Hemisphere land-air temperature during the past 130 years.
So they're talking about the there's basically an 11-year sunspot cycle. That's the shortest solar cycle we know of. But then there's a corresponding 100-year rough, like they're saying 80 to 90 years here. There's a century-long cycle that kind of goes up and down. But then there might be 500-year cycles, 1,000-year cycles that we don't know about yet because we haven't been tracking it long enough. There's probably 50,000-year cycles and 100 million-year cycles. You know, the sun can have, who knows?
Yeah.
So.
Well, here we have a possible solar origin of the 1,470-year glacial climate cycle. Demonstrated in a coupled model. So there you go, Russ. You were anticipating. Major paleoclimate records from the North Atlantic region show a pattern of rapid climate oscillations, the so-called Dansgaard-Eschger events, with a quasi-periodicity of approximately 1,470 years for the late glacial period. Let's see, there is whereas pronounced solar cycles of approximately 87 and 210 years are well known, a 1,470-year solar cycle has not been detected. Here we show that an intermediate complexity climate model with glacial climate conditions simulate rapid climate shifts similar to the Dansgaard-Eschger events, and so on. Let's see what then says. Evidence for solar forcing of climate change at circa 850 calibrated years BC from a Czech peat sequence. A climatic change to wetter and cooler conditions, which was recorded in the Hancock Lucha peat sediment in the giant mountains of the Czech Republic at circa 850 calibrated BC. The curves of climate indicators were compared to detrended delta carbon 14, which is considered to be a proxy for solar activity, to assess if solar activity through changes in, for example, irradiance had caused the observed climate change. So visual comparison of the curves showed that changes in the bog and in the regional vegetation occurred in correspondence with the start of the sharp rise in radiocarbon at circa 850 cal BC, caused by a sudden shift to low solar activity. Geophysical, archaeological, and historical evidence support a solar output model for climate change. This is from the year 2000. Let's see what else here. Climate and solar variability recorded in Holocene laminated sediments, a preliminary assessment. And their assessment says that the sediments of Loch Ness appear to contain a record of the influence of the North Atlantic Ocean, and via that, solar variability upon the climate of northern Scotland spanning recent centuries. So, I will stop to share there. We could go on and on and on. But we don't need to consider the sun as a factor in climate change because we know that it's all carbon dioxide caused by people driving SUVs and other things.
I don't know. The most obvious climate change cycle that I've noticed is like the difference between day and night.
Yeah, it's pretty severe.
Yeah.
30 or 40 degree changes sometimes in a matter of hours.
And I assumed that it was because in the morning everybody got up and got in their cars and drove
Went to work.
somewhere.
Well, yeah. Well, Kyle, have you ever noticed this one too? The cycle between summer and winter. It's warmer in the summer and colder in the northern hemisphere winter. Have you ever noticed?
Yeah.
Have we noticed that?
Now that you think about it.
Now that I think about it, yeah.
Well,
I also noticed that the sun is lower in the sky when it's cold.
Yeah. I just thought of it as hoodie season. I didn't realize it was an actual winter.
uh-huh.
Yeah.
Well, we live in Texas. You know.
Time to break out your hoodies.
Yeah.
Okay. Well, so where should we go from here? I think we've established that the sun is a very important player in climate change. I think at this point, there's overwhelming evidence. Yet, we're now in a situation where we're in the middle of a climate crisis that is exclusively being caused by carbon dioxide. So one has, I think, to ask questions here about this whole thing because...
wouldn't it be fair to say that the sun is the only player? Pretty much, like in terms of scale, that everything else that's involved is so minuscule compared to the sun.
Yeah, I would say that the sun, to me, I wouldn't say it's the only, but I'd certainly
it's
say
like the primary driver.
The dominant one, yes.
Yeah.
So if
it
we're
seemed
ignoring...
like a simple mental exercise, remove the sun from the picture, and the Earth becomes a static, solid ball of ice, including all the gas, is frozen, and then nothing changes. It'll stay the same, right? It doesn't matter how much CO2 you've got, it's still frozen solid. It isn't going to be any warmer if you have a bunch of CO2. When you add the sun, now that's where all the energy is coming from.
Yeah, ultimately, that's where the energy is coming from. Yeah.
Yeah.
So here's a paper that appeared in 2001, also in Science. And it kind of puts a little context here. Richard Kerr, who's a science writer, this is what he says. And this is referring to new evidence that's coming out because by 2001, we're starting to get the data from solar observing satellites, right? So, quoting from the article, and here's the article title: "A Variable Sun Paces Millennial Climate." Most scientists have long assumed that the sun shone steadily, its unvarying brightness, the one constant in a climate system that seemed to lurch willy-nilly from one extreme to another over the millennia. From time to time, a few brave souls would suggest that the sun actually waxes and wanes with a steady beat, driving earthly weather or climate in predictable cycles. In a paper published online this week by Science, paleoceanographer Gerard Bond, who we just quoted of the Lamont, or who we just referenced, of the Lamont Doherty Earth Observatory in Palisades, New York, and his colleagues report that the climate of the northern North Atlantic has warmed and cooled 9 times in the past 12,000 years, in step with the waxing and waning of the sun. Quoting glaciologist Richard Alley of Pennsylvania State University, "It really looks like the sun has mattered to climate." The test for a sun-climate connection comes when the two types of records are put together for comparison. The more in sync the sun and climate are, the more it looks like the sun is driving climate change. Quoting Bond, Gerard Bond, "It's a strong result. You can do statistics on it." End of quote. But what really persuades him is what you see in a plot of the two records, the close match between the peaks and the troughs of the climate record and those of the solar record. Simple analysis gives a correlation coefficient between 0.4 and 0.6. Quote, that's a very high correlation for separate geological records, says geophysicist Jeffrey Park of Yale University. It's not on the margin. It shows that the connection is real. As warm as the reception for a sun millennial climate link may be, researchers caution that much is left to be sorted out. Quote, it remains a little hard to figure out exactly how the sun has mattered to recent climate and why it has mattered so much. Now, again, this is in 2001. So clearly from this, we can say that it's now being recognized by the turn of the millennia, in the turn of the century, that there is a very profound role for the sun in climate. Yet we've been hearing for over 2 decades now, even going back to 2001, that the science of climate change is settled. And this is why I say anybody who says that is really just confessing their appalling and abysmal ignorance of the science of climate change. And they're just regurgitating the propaganda that they've been spoon-fed through mainstream media and mainstream academia. And now we have a whole generation of kids out there, and young people and older people too, who should know better, that we're in the middle of a climate crisis. And the only way we can solve that crisis is by going out and gluing ourselves to the interstate.
Okay. So let's, what would you say I'll play the devil's advocate. Like, okay, the sun is a big factor, but what we're talking about here is CO2 trapping the sun's already existing heat. If it gets more intense, we're just going to trap more of it because we're putting all this CO2 into the atmosphere. And the results of that is going to, quicken the point at which that the Earth heats up too much, and the rest of the ice caps melt, and the sea levels rise, and we have all of our cities flooded, and mass movements of people, and all the devastating, terrible things that follow. So what should we do? Like what you're talking about, if you're saying the sun is the main driver, then we have there's nothing we can do. So are you saying we should do nothing? Well,
the first thing we should do is make sure that we've hardened all our systems to at least the low-level events like the Carrington event. I don't know what we would do to, something on the level of the 14,300 event. I don't know what we would do. But that needs to be part of the discussion. If I'm saying anything with certitude, it's that those kinds of things need to be part of the discussion and not eliminated from the discussion. Does that make sense?
Because so are you suggesting that that's kind of what I'm getting at? Because my thinking is in line with your thinking, but I'm trying to figure out to a person who believes all this stuff, and because number one, you have to believe that CO2 is the actual problem. Us releasing CO2 into the atmosphere, that's the problem. And then what the problem is actually going to cause to happen is also going to be devastating, like this warming. So if you go and make the argument to people that, well, it's the sun's variability and it could get hot real quick or cold real quick, the problems still exist of that change, right?
Yeah, well, if on the other hand, the cycle is such that we should be going perhaps into another cold phase, then additional warming, because we have increased the greenhouse gas concentration, may actually be a good thing.
Right.
So you're saying our carbon pollution is saving us from another ice age?
Well, I don't call it, if it's carbon monoxide, we could call it, but carbon dioxide is not pollution. That is, you can't call that pollution any more than you call oxygen pollution.
Which brings up another question. Maybe I've asked this before. We complain about all the internal combustion engines creating carbon CO2 exhaust, yet every mammal alive exudes CO2.
Kill all mammals.
So that's really? Is that true?
Well, no, it just if the logical extension is to eliminate internal combustion engines and these sources of CO2, what do we do about all these mammals that are in the way?
Yeah, you are the carbon they want to reduce, Mike.
You are in the way.
Yeah.
Yeah, Mike, you are one of those mammals. I don't know if you're realizing, Mike, you are a mammal.
No,
I mean, I definitely believe that it's anti-human. Like the whole movement seems to be like less humans, stop being awesome. But I'm not. My thought is like, how do you convince somebody who's not driving the agenda, but because they're not going to change?
Who's invested in their belief, you mean?
Yeah, just a person who's actually, just not a driver of the agenda or the narrative, but just somebody who's consumed all this and believes it. To tell them, well, it's not you, it's the sun, and we're all screwed. I guess I'm asking you to approach it in that way. How would you approach?
Well, I mean, the first thing I don't know how you go about this, but the first thing you'd have to educate them because they're not educated on the science, and so that's why they're susceptible to the propaganda. But I mean, you can show, and we've discussed it actually pretty extensively in this podcast, actually, as far as the role of CO2 in the climate. And I think what I'll do is I will just share a screen again here.
Well, let's go back to the statement that CO2 is not a pollutant, and it unfortunately has been tagged as a pollutant. When you're right, it's one of the essential gases in the atmosphere.
Yes.
From some of the stories I've read, methane is as big or bigger a problem than CO2.
Mm-hmm.
Methane is generated in all kinds of different ways, whether it's swamp gas or landfills leaking or permafrost thawing out.
Okay. Well, this graph right here, I think will kind of perhaps settle the matter. I hope we're seeing this right. That shows
Yes.
the carbon dioxide contribution to the whole greenhouse effect. So down here on the bottom, we have parts per million of CO2. I should probably put this on. Let's see what happens. Are we still seeing it?
Yeah.
But in presentation mode? Okay, good. So over here, you have the net downward forcing in watts per square meter.
What does that mean?
Well, watts is just an amount of the energy.
What does downwards forcing mean?
That means that what's happening is, the sun's radiation comes in, passes through the atmosphere. It's a shortwave radiation. It's absorbed into the solid material of the earth, and then it's re-radiated as long-wave radiation. So that long-wave radiation is now emanating back out towards space in a wavelength of about 15 or 16, 17 microns. Okay, so that is the capture window of carbon dioxide in the atmosphere. So what happens is when that longer wave radiation comes against that insulating blanket of carbon dioxide, some of it is reflected back to the earth. In other words, reflected downward. It's forced to go downward. Other parts of it emanate out through space because that capture window is virtually saturated. So its ability to capture additional heat by exciting carbon dioxide molecules is limited. But some of that, particularly in the lower regimes of carbon dioxide, like the first 100 parts per million, a lot of the long-wave radiation is reflected backwards towards the Earth. And that is what is thought of as the greenhouse effect. That's what's heating the lower atmosphere. Does that make sense now? So that's what that means, net downward forcing in watts per square meter. And so you can look at this graph here, and what you're going to see is that from zero carbon dioxide up to 100 parts per million, the net downward forcing is up to 200, what is this, over 250 parts, or 250 watts per square meter. And if you look at the increase in the reflected heat that's forced back to the Earth, back to the lower troposphere, you're going to see that it follows a logarithmic curve. So you'll notice that the forcing between 0 and 100 is a whole lot more than the amount of radiation that's reflected back to the Earth between 100 and 200. And when you look at again, between 200 and 300 parts per million, the amount of radiative forcing is reduced even further. And as you come up the scale of CO2 concentrations in the atmosphere in parts per million, what is happening is that radiative flux that's being returned to the Earth is diminishing according to this logarithmic curve. So that each increment of increase of CO2 in parts per million, the amount of radiated heat sent back to the Earth diminishes logarithmically.
You mean the increase in the amount, right?
That's what you're saying. Increase in the amount of CO2.
And the increase in the amount of returned heat. So
returned heat, but that increment of returned heat is diminishing. If we look at another version of this,
the increase is diminishing.
Yeah, the
rate of increase.
The increase is diminishing.
Thank you. The rate of increase is diminishing. So I'm going to. The next slide is going to change the y-axis here. Okay, so here we're going from 0 to 250, and here you can see the curve. At 0, almost to nothing, is where most of the heat capture happens. And you can see from here, it levels out to be almost insignificant after about 300, 400 parts per million. And check this out. If we look at this blue here, that's the forcing, the blue curve. And then you have the red is the amount of CO2 in the atmosphere pre-industrial times. Present, now this is too low now because it's come up to just over 400 parts per million. And then doubling the pre-industrial is this line right here. So take a look at what happens between 0 and pre-industrial, the amount of increase of heat transferred back to Earth compared to what has occurred or what would occur between pre-industrial and doubling of pre-industrial. It's insignificant. And the reason is because that window, like the main greenhouse gas that already occupies that window is water.
Yeah.
And that's the problem. See, this is the thing and so how do they get around this is by tweaking the computer models and introducing these positive feedbacks, self-amplifying positive feedbacks to get around this logarithmic curve. Here's another way of looking at it. Go ahead. Yeah.
Well, the reason why I asked you this question about the sun, like how would you talk to a normal person, is because I've used both of these arguments before to try to, talk to somebody about this who isn't aware.
And what is
this whole argument with the CO2 capture, being basically saturated, not totally saturated, but close. And then also the variability of the sun, it doesn't have any effect. So
is
that's
that
why.
That's what they say.
I've never had any success with it.
Or you mean the argument doesn't have any? The argument doesn't have any effect.
Yes.
Well, because you're dealing with a religion, you're dealing with a religious belief as opposed to a rational belief.
Well, let me ask you this: do you get any kind of response at all? Do you get a counter argument from people that you've talked to? I'm just curious.
Yeah, it's usually appeal to authority or something like that. It's like, it's a consensus of scientists. You're going to argue with all the scientists, that sort of thing.
The most honest response I got to using these arguments is they said, well, do you suggest we just do nothing at all?
Yes.
But in other words, they're saying, so if we're not causing it and it's the sun or whatever, it's natural processes, that means we can't fix it. So what are you suggesting? We just all die? Because we know the climate is changing. That's what I'm saying. What they ask.
But what I'm saying and what I would say to them is, no, there's no problem that needs to be fixed.
Yeah. Yeah.
It's imaginary. There is no problem that needs to be fixed.
And like the history of, life on Earth is you adapt to the changes, right?
Yes.
And
excellent point.
My suggestion is usually, and this doesn't has never worked, but I'm just like, no, we need to become more awesome, right?
Yeah,
like if there's
yes.
going to be actual drastic climate change that could kill us and a bunch of animals, the only way to fix it is for us to have better tech, more power.
Yes.
And then we can save the animals and maybe ourselves, you know?
Yes.
Yeah, so
Yes.
I like your initial response, which was we need to start hardening the grid. We need to do all these things that don't have anything to do with CO2.
Correct.
Right.
Yes.
And there's plenty of, there's plenty of environmental stuff that I love, like cleaning up trash in the water, in the oceans, like cleaning up the air is great.
Yes.
All this, and this is, and local efforts. Like we have people here just in our area that they take time off on their weekends to walk up and down the local roads and pick up trash, right? This is the kind of stuff that's fantastic and where you can have an effect.
Yes.
Take it
and
somewhere out of sight and bury it.
Yeah. Throw it in somebody else's yard.
Well, Texas has a lot of room. Couldn't we just take all of our trash to Texas?
We got, you come dig out in the desert, bury it.
I'll sell you 1 million acres for $1 million. You can put all your trash here.
So listen, I'm totally 100% about, getting this, cleaning up the environment, the pollution, and absolutely. But to me, what we're doing is we're shifting all of this money. When you think about, okay, if we're going to go green, which means solar and wind, I mean, the pollution that's going to be generated is a byproduct of that, because when you start mining cobalt and lithium and iron and all of the materials that need to be extracted, and then you've got billions of tons of stuff that you're going to have that have a lifespan of 15 to 20 years. What do you do?
I saw one story not long ago about wind turbine blades.
Mm-hmm.
They wear out, and they don't know what to do with them all. I mean, they're what, a couple 100 feet long?
Yeah, there's a graveyard of wind turbine blades.
My idea is to build a wall.
Build a wall with it.
They're like giant spikes sticking up.
And I know the impetus is for electric cars, but what do you do with all the batteries? The batteries have a certain life, and what do you do with the car when it becomes too expensive to replace the battery, and you got what, a 10-year life on the battery, and the car's dead. You can't sell it for anything. You got to replace a battery for 10 or 20 grand. That's not a solution either.
Well, this is true. Of course, now we haven't really talked about this much. I mean, we have a little bit, but a lot has changed since the summer with the whole plasma energy thing. And it has now had multiple major testing done. The Zurich conference that our good friend George Howard was just at, the plasma generating technology, the plasma technology was tested there. It's tested in a major industrial laboratory affiliated with one of the major research institutions. Not too long ago, a couple of months ago, that I had the privilege of participating in and seeing for myself the testing of generators. There's now the London build out, where there's the first really industrial scale application of the plasma technology to a 300 kilowatt Pierce generator that is part of a substation that feeds into the London power grid. And that has now been recently approved by the officials of the London power grid to contribute, and it is now integrated to the London power grid. This is the first. The Tesla Tech Conference also showed that it works, and there's also tests now going on in Germany as a consequence of the conference that was held in Zurich, where the technology was also demonstrated. So I'm going to show you one of the readouts from one of the tests, and this is very consistent. That's what's getting across the spectrum.
You want to take a break before you do that? We're about an
Sure,
hour
I was gonna say
in. If you're gonna get into that a little bit more, let's wait till after a break.
Let's do a break. Sounds good.
All right, we'll be right back.
All right.
back, folks.
Oh, we're not.
We're
I
in the
thought
middle
we were.
of a serious sea. Well, no, we were. We were already back, but I'm just saying it officially.
Oh,
We're in the
okay.
middle of, we got back on the climate change topic, but we are going to be moving to some of the technology, I suppose.
Well, it would be a good.
We got
segue.
derailed off the sun. The sun was great, but we're moving on.
Well, we're not really moving on, and here's why. Because the sun is plasma.
Plasma.
Plasma is the key here. And I'm beginning to realize how mind-boggling this whole concept of plasma is. I mean, a few years ago, I knew basically nothing about plasma, other than that it was the fourth state of matter, and that it resulted when you had this enough energy introduced into a molecular or into an atomic system that you had complete disassociation of electron and proton. And unlike the other three states of matter where there is a bond, even though in gas the bond is very weak, there's still a bond. But in plasma, there's no bond. And somehow when that happens, that's when the magical forces take over. The things we can't explain. But so I was going to show you an interesting graph here.
I think there's no bond because the electrons are like they get decoupled from the nuclei. Right?
Exactly.
Yeah.
That's exactly it. And it's when in that state of basically infinite degrees of freedom that something happens, because in that state they are susceptible to being influenced because of the fact that it is electromagnetically conductive. And
yes, that's right. Yeah.
Yeah, they're electromagnetically conductive and therefore can be influenced by means of electromagnetic containment fields. And I think that's what's at the heart of this, of any technological system that would be developed using plasmoids. But in the one of the reasons I've been hesitating to talk too much about what I'm learning there is because, initially I did talk about it. A lot of the people criticizing it, and, basically the skeptics were saying, well, have you personally seen it? And my reply would be, well, no, I haven't personally seen it, but I've talked to people and I know people whom I trust that have seen it and have witnessed it, but I myself have not. However, as of last summer, that's not true anymore because now I have seen it. I have witnessed it firsthand. I've seen two generators, one outfitted with the technology, one not. I've watched the two generators being calibrated so that the effluents are precisely adjusted the same. I've watched the retrofitting of one of the generators. I've watched multiple people coming in with gas analyzers, mass spectrometers, using multiple cross-platform ways of testing what's happening with these two generators. And so I was there for a weekend and was able to watch the whole process and then the testing of the process. So what I'm going to do here is I'm going to pull up a screen share. Let me, okay, so here was one of the tests that I witnessed. Let's see, here we go. Okay, this was the Honda generator set, genset, one cylinder, 0.38 liter or 38 cubic centimeters petrol test or gasoline. The aim was to compare the Honda genset one cylinder engine running petrol or gasoline without the MSAT technology, which was the baseline, compared to operating the engine with MSAT technology. The baseline is taken without having run the MSAT technology. The Australians pronounce it MSAT, so I'm going to pronounce it that way. The baseline is taken without having run the MSAT technology. This is because once the energy is infused with plasmoids, the MSAT technology effects partially remain with the engine when the MSAT technology is not powered on. So there was a whole group, George Howard was there, and there was a whole group of, these were industry professionals, scientists. There was a physicist or two there. There were engineers. There was 11 people. Okay, and this is the equipment that they had for the testing. The testing, when I was only there for the first weekend, the testing went on for a whole month, testing various iterations. Okay, so you had infrared temperature sensors, air temperature sensor. Let's see, water temperature gauge, water for the scrubber, the bubbler. I'll show you that in a minute. What the bubbler is, that's the component of the technology that actually creates the plasmas that are being harvested into the thunderstorm generator. An RPM meter, gas gauge, gas quality sensors, vacuum gauge, pressure gauges. There was also, these were the cameras present. There was a still camera, an isolated video camera to run uninterrupted from 30 seconds before ignition until 15 minutes after shutdown. There was a Caterpillar FLIR thermal imaging camera, slow motion camera for use on the plasmoid generator. And then you had, these were the gas analysis package. So you had the Kane International 5-gas analyzer, because that's, let's see, carbon dioxide, carbon monoxide, nitrogen oxides, oxygen, and then miscellaneous hydrocarbons. So those are the 5. That's why it's called the 5-gas analyzer. Land logical engine exhaust. So now here's what happened. So one of the generators is retrofitted. It's run. In fact, they're both running. They're in separate rooms. They're both running, right? One is now, they're both started at the same time. The technology is retrofitted onto one, but it's not turned on yet, right? So now you're running the 2 generators simultaneously. And then after after a couple of minutes, whatever it took to warm up the generators, the technology was turned on. And now you've got the probes into the exhaust pipe of the generator and a mass spectrometer, which are reading whatever's coming out of the exhaust of the generator. Okay. So, and this is the same thing that happened at the Tesla Tech. Pretty much, I think they were testing the same kind of a generator there. They had it inside the room up on the stage. Mike Robertson was out there, and they were live streaming this thing out to hundreds of people who were watching it real time while they videoed and recorded the building of the retrofitting of the generator itself. They started it up on the stage, testing it without the technology, and within a few minutes, the fumes from the gas was getting so strong that they had to turn it off and move it outside onto the loading dock. And then they restarted it on the loading dock. And so the actual testing took place out on the loading dock, because otherwise they'd start asphyxiating the people in the room. Okay. And I think that they had the same type of generator as they did. This is the one that I witnessed here. Okay. So now here's the results. Okay. So this was on July 3rd, 2023 at 11 minutes after 10 in the morning. The reading was 9.3% carbon dioxide coming out of the exhaust. It was 5.48% carbon monoxide. It was 4.66% oxygen. And in terms of parts per million, there was 199 parts per million of hydrocarbons and 27 parts per million of nitrogen oxides. Okay, so now at 10:15, roughly 4 minutes later, after the technology has been turned on, look what's happened to the carbon dioxide. Now, I stood there and watched this on the meters, watched it going down from 9.3% to 0. Okay, carbon monoxide, 5.48%. Within a minute, 0. Oxygen from 4.66% up to 20.97%. Hydrocarbons, 199 parts per million down to 58 parts per million, and nitrogen oxides from 27 parts per million down to 4. Now, what the hell is going on there? Now, I don't know if you guys realize how truly extraordinary this is, because something has happened here. And I think that the only way we can wrap our heads around it is to recognize that what happened here is alchemical, that there was actually a transmutation on an atomic level. And I was there when you had 8 or 9 scientists from all over. There was a scientist from India. Who were they? I mean, there was a bunch of them. You had industry professionals. So I'm standing there while all of these guys are scratching their head going, what the fuck are we looking at here?
So it looks like, I mean, I don't know anything, but I'm just saying, just from these numbers, it's like it's freeing up all the oxygen from those other compounds.
Mm-hmm.
And then somehow those other compounds are the carbon.
Mm-hmm.
And you know, because if you take hydrocarbons, you got the carbon in the hydrocarbon.
Yep.
You got carbon monoxide and carbon dioxide. So you get all the oxygen off of that.
Mm-hmm.
Roughly, just with the CO2 and the carbon monoxide, that's roughly 15%.
Mm-hmm.
And
well,
then you have roughly
yes.
5%. So you end up around 20% oxygen coming out. So what's happening to the carbon? The carbon is not coming out.
Yeah, what is happening to it?
Is it getting welded to the inside of the engine somewhere? Carbon deposits? Where is it going?
Well, that's the question that a lot of people were asking. And yeah, a lot of the subsequent tests were about addressing where the hell did the carbon go?
Yeah.
But it ain't coming out of the tailpipe. So is it possible that somehow the carbon dioxide and carbon monoxide are atomically transmuted into oxygen? But here's what's interesting.
That seems the least probable to me, but.
Well, it does seem the least probable, but what is happening? I don't know. But here's another interesting and curious thing. 20.9% oxygen. Now, this is air. I mean, the rest of it, what's coming out is air, primarily nitrogen and with argon and other trace gases. But this, as it turns out, is the optimum percentage of air or of oxygen for pure, pristine, unpolluted air. 20.9%. I mean, that's like within a few tenths of a percent of what would be considered the optimum oxygen in air.
For what?
For breathing.
To breathing?
Yeah, if you're
breathing?
Yeah,
Okay.
George Lush used the analogy. He says, if you were out in an alpine mountain meadow, flowering alpine mountain meadow, breathing the purest unpolluted air, it would be roughly equivalent to this. The air that's coming out of the tailpipe. So that's pretty wild.
Yeah. Great. So no more suicides in the garage with the car running.
Well, this could put an end to that.
You know, I'm Randall. I'm not sure I buy the whole alchemical business, but
well, you don't have to buy it. Nobody knows. Nobody, professionals are scratching their head trying to figure out what's going on here. I'm just throwing that out as a possibility, whatever that means.
And there's the problem I have. If the guy who invented it doesn't know what it's doing, then there's a problem. So
look. When Leo Szilard figured out that you could fission an atom, he didn't know what the hell he was doing. He didn't know how to explain it, but it was real.
Yeah, I agree.
It took teams of scientists 5 years, 10 years later to figure out what was going on. He didn't know.
Yeah.
So I mean,
that's totally true.
It doesn't matter if he doesn't know for sure what's going on, but something's happening.
Yeah.
Yeah, exactly. That's what it is.
I also wonder, you can't, I'm looking at what Kyle was talking about with, you've got this, it's basically 10 with the CO2, and we'll just round everything 5 with the carbon monoxide, and then 5 with the oxygen. You can add that up to get roughly 20, but it's
Not
CO2. O2.
Yeah, O2. There's 2 oxygen atoms.
And then CO is only 1 oxygen atom. And then I guess the oxygen they're actually reading would be O2. Yeah.
Right.
So the numbers don't actually add up totally correctly, I don't think.
But so
But it is
You're right,
interesting.
hydrocarbons and
Where's the
nitrous oxide.
carbon going? Like if at basic you basically say, well, it's cracking the carbon away from the oxygen, and then we're seeing the oxygen come out of the exhaust.
Which happens with what is the process? The
electrolysis.
The electrolysis, which
Yeah.
the bubbler thing and the ionization.
Electrolysis breaks apart hydrogen and oxygen. Yeah.
Well, yeah, but if you can, it'll break other bonds as well.
That's right. Yeah.
Depending on what the solution is.
It seems like you're probably right. It's not only breaking the carbon, but it's breaking the NOx as well. It's breaking all the oxygen bonds.
Yeah, and
so it's like a
and
redox reaction.
Oxygen bonds can be weak. It depends on how it's bonding, but it can bond weakly. So
where's the carbon going?
Yeah, that's the question: is what's happening to the carbon?
It's falling out in little black pebbles, and the meters aren't reading it. They're just like dropping it. There's black dust all over the floor.
I like your idea of it's welding itself to the inside of the engine. Huge carbon deposits on the pistons.
Well, they've been looking at that. I'm pretty sure that's been part of their testing protocols, trying to get to the bottom of what's happening to the carbon.
Yeah,
because that's been the first question that arose, and now you've got a whole team of German scientists who are looking at it subsequent to the Zurich conference, and so we'll see what happens, what they come up with there. And I imagine some Swiss scientists. I don't know. There was quite a few people at that Zurich conference, probably 100 to 150, mostly professionals in one capacity or another. George Howard was there. And so there's some funny videos of George Howard getting down and huffing the plasmoids. He did it. He did it in Albuquerque, and he did it again in the other place, the industrial laboratory.
I could totally see
it.
Yeah, man. Sounds...
Let's breathe them in. Come on, taking me some plasmoids home.
I was there, watched them get down there and start sucking on that exhaust pipe.
George is
classic. That's great. I have been following the
updates,
and seeing people run the tests on the with the meters and stuff, and
building
prototypes. It's cool. It's good to see.
Have you guys watched Alchemical Science with Jordan? I don't know his last name, but he's put together a do-it-yourself guide how to build it. And he's got you have or haven't?
Have not.
Check that out. Yeah, I mean, what he's doing is pretty cool. He really gets into it. What he's doing is great. And then, of course, there's Gary Ling over in England, who's got the what's it called, ballsy thinking, something like that, where he's got, he's been there at the London build-out. He recorded all of the stuff that went on at the London build-out. Oh, by the way, Johanna James went down and visited the London build-out just within the last few weeks.
Nice.
So she's now very interested in it. She's probably going to be talking about it quite a bit on her podcast. And I'm thinking I would like to let Graham Hancock know. I mean, he'd be welcome to visit and get a tour. The thing is right now it's the team there is not there at the time now that was doing the testing on it. Apparently they're going to be coming back around. I don't know when. So the time to go there would be when the build-out team is there, whatever the next iteration of the testing is.
So a big question to me for this, I mean, obviously this is going to happen, but, running a generator for an hour or so, but can you put 4,000 to 7,000 hours on it? How much
with
maintenance
loads.
does I know they are doing loads, because I remember one of the tests, they set up all these lights and they were running so that the generator was working hard. But one of a big thing for us, like, farming stuff, when you buy a machine, you need to be able to
run for 70,000 hours.
70. I mean, I'm happy with 7,000.
That's 7,000, yeah.
But how, they all take maintenance. You always have to maintain them.
Of course.
Things break down, all that kind of stuff. So, so there are some machines that just for whatever reason, they are always needing more maintenance. Maybe it's engineering, whatever. It's like things are breaking. They're really annoying. Get rid of the damn thing. Get something different. So the question to me is like, okay, if it does this and it improves the
power output.
Yeah, the power output and the efficiency of the engine, will it sustain that with minimal maintenance?
Good question.
If it only runs for 1,000 hours before it's like, because like for example, you can put really low viscosity oil in your vehicle and increase the efficiency of the engine.
Sure.
Right, the gas mileage will go way up, but you also burn up the engine.
Yeah, its lifespan
drops. So like you use a high viscosity oil and you can increase that lifespan, but you lose some efficiency. So that's a big question.
It's a good question. And I'm quite sure that is one of the questions being addressed.
Oh, I'm sure. Yeah. These are things that
they
take time.
They take time and they have to be done. Like, just turn this generator on and run it nonstop. For 1,000 hours or even 100. Like, let's see what happens to it and then take it apart
with the other one without it.
Yeah.
Exactly.
But yeah, it's great that this is happening. It's been cool watching these guys, building prototypes, and I've been following Nikita. He's been doing great work.
Yeah. Have you he's got a good report out now. I'm about halfway through it. I'm working my way slowly through it. I'm, doing a lot of additional auxiliary research as I go through to understand stuff better that he's talking about. It's a lot to unpack, but
sure.
I met Nikita. He was there. He was one of the people there. So anyways, it's exciting. I don't know what the outcome of it's going to be in the long term, other than it certainly seems to have potential.
Yeah, it's doing something very interesting.
Yeah, absolutely.
That's for sure.
And you guys, well, we've all had a front row seat.
Yeah.
Brad has been intimately involved with helping to get some of the presentations together that have been now used to present some of the ideas to these various groups of people who. So
yeah, George actually invited us to come out to that one of those tests, not the Tesla one, but the one that happened after. But we were in the middle of harvest, so we couldn't go.
Right, that's the one that I was at.
Yeah. It would have been great, but we can't do anything else but harvest grapes during that period.
Yeah, that was a rough time.
Yep.
It was great, but
well, I'm sure there'll be other opportunities. And now what we got is a bunch of backyard mechanics who are, really interested. They're, Jordan over there at Alchemical Science has got a whole, dialogue going with people who are now going to make the attempt and who are attempting to reconstruct the technology. And so he's got the schematics up there. There's the three components basically to it. You've got the pre-ionizer, and then I still can't say I thoroughly understand what each one does, but I'm learning. The pre-ionizer draws in air when the on the vacuum stroke of the piston in the generator sucks in the air into the pre-ionizer, and there's an ultraviolet bulb in there that radiates at about 300 nanometers wavelength. And then what that does is, if I'm understanding it correctly now, it pre-ionizes the air, and it excites the electrons, which makes it easier at the next stage, which is in the bubbler, to create the dissociation that yields the plasmas. So it's fed from the pre-ionizing chamber into the bubbler. At the bottom of the bubbler is a diffuser stone, the same kind that you use in an aquarium, right?
Yes.
And you want to
create microscopic bubbles.
create microscopic bubbles. Exactly. So they're coming up. And then there's like, he's using steel wool that apparently creates shear that helps to sever the bubbles and make them smaller and smaller and get them to microscopic. Apparently that helps after they're coming out of the diffuser. And then on the compression stroke of the piston, the small bubbles, and it's only the microscopic bubbles that are symmetrical enough that when they collapse, the North Pole meets the South Pole. Okay. And then that creates the geometry for the plasma. It creates that toroidal geometry, which is the geometry for which the plasmas have this affinity for this toroidal shape. So somehow, and I'm still trying to wrap my head around exactly what happens then, how the plasma that's being generated in these collapsing cavitation bubbles is now being harvested and then being fed into the thunderstorm generator. And you've got you've got a concentric spheres connected by concentric pipes. And it works very much on the principle of the Rank-Hilsch vortex tube. And you guys have looked that up, right?
Yeah.
It's these two opposing vortices, one inside, the cold one inside one direction, the hot one on the outside. And somehow it can pull apart air of room temperature and get as much as over 300 degrees difference between the hot end and the cold end. This was one of the things that really mystified George Lush, because he was there with his heat analyzer, and he couldn't believe the temperature changes within the thunderstorm generator and in the pipes over just 6 inches, 7 inches. And he talks about that in the interview that's on that Gary Ling has on his website. He's got the interview there with George Lush, which is really interesting. So now you've got the thunderstorm generator, and you have a pipe coming into one end, which is the input, and it's geometrically, it's in such a way that the gas coming in is tangential to the sphere, which sets up the swirl. So there's a swirl chamber that's in the sphere, just like there's a swirl chamber in the vortex tube. And somehow it's the geometry. And this is the part I'm trying to really get my head around now, is how this thunderstorm generator works. And unlike the Hilsch vortex tube, where you actually have a vortex of cold air inside the vortex of hot air, rotating in opposite directions, but are not actually in full contact. However, there is an electron exchange between the two. But in the thunderstorm generator, they're actually separated by a pipe.
Yeah.
So you've got
that too.
Yeah, you got an inner pipe and an outer pipe. So you have a swirl in that space between the inner pipe and the outer pipe, the outside of the inner pipe and the inside of the outer pipe. And the same thing with the concentric spheres. And they have to be in the ratios of 4:3:2, which I find very interesting when you think about it, for multiple reasons. The length of the pipe between them is critical. It has to be a harmonic of 144.
And I wonder about that. Like, were a bunch of different lengths and sizes and proportions tested, or was it just like
because they've made different size thunderstorm generators. Yes, they have. In fact, there's a list of 5 of them that have been made. They're all close, but they're different sizes, different ratios. And I don't have that handy at my fingertips, but I do have it. So it seems that there's an optimum ratio, and that optimum ratio is 4:3:2. So if you got a 24-inch sphere, then you would have an 18-inch sphere, and then you'd have a 12-inch sphere inside that. But when you add that third sphere in the third pipe, apparently what happens is the implosive powers really get considerable. And they did test one. You've probably seen the photographs of the 6-inch steel pipe that was ruptured.
Yeah.
You can see, yeah.
It like
So that
collapsed.
It collapsed, yeah. Now it imploded and literally ripped through the steel. So they decided they didn't need the third pipe.
Yeah,
So-
it's interesting too that it's utilizing bubble cavitation, which is using the engine compression and rarefaction to create that, which is cool.
Mm-hmm.
And bubble cavitation, like sonoluminescence, is a cause of that. Like it gets so ridiculously hot when that bubble collapses inside the air of the bubble. And I looked at a lot of different studies of people doing experiments with sonoluminescence where they would have like different liquids, like it was like xenon gas or some gas bubble inside some.
Probably, I think they used argon gas.
No, this was
this
is a specific. It was a weird setup where they just had they had a big cylinder, like a piston inside a cylinder that had this liquid in it, and they put one bubble in there, and then they just dropped the piston through the cylinder, and bam, it hits a solid steel floor and collapses that bubble. And they were just trying to get the hottest temperature inside the bubble that they could. This is like they did all these different things. So I've always been fascinated by that, by the potential in that in bubble cavitation or sonoluminescence.
Mm-hmm.
So it's interesting how it's being utilized here. It's it can be very destructive too. It'll eat away it'll just like eat into metals.
Mm-hmm.
The cavitation bubbles.
Yeah, and where I've encountered cavitation bubbles is in turbulent water flows.
Mm-hmm.
And they probably play an important role in
destroying rocks
and creating potholes.
Yeah. Yeah, when we were in Montana, that giant turbine from the dam, the first dam we went to, did you ever go and look at that closely? That huge turbine that's what's the name of the park? When we walk up to the overlook where the
Cabinet Gorge Dam. Yeah, there's a big turbine
blade. There's a huge turbine blade there. And you can see where they had taken it out probably multiple times and just welded stainless steel
material,
adding material onto these blades, and they were just being eaten away. I mean, it's like something is just eating away at this massive stainless blade, and I'm pretty sure that that's what it is. It's a lot of it is cavitation.
Yeah, they had this same problem with submarines.
Yeah.
Does this go to what you were saying earlier about the reliability or longevity of the engine?
Well, I don't know because I don't know where. I think the cavitation is happening inside
if it's contained. Yeah.
Wherever they have it. I know I've seen some of the images. It's happening inside like a glass or maybe even a plastic tube. They're looking at it. But
yeah,
I don't know what
the cavitation with the turbine blades. It's happening at the interface between the water and the metal.
Yeah,
that's how does that erode the metal?
Well, there's different because the bubbles don't all collapse perfectly symmetrically. So when they're close to a surface and they collapse, they can get these what they call, I can't remember what it's like, it's a spike. So it kind of collapses and then this jet shoots out of one end of it.
Like a hot jet.
It's microscopic.
Yeah.
This jet is really hot.
Trillions of them happening.
Really hot compressed gas is spiking out of this side of this bubble.
Is it the plasmoid that Randall is talking about?
I've never heard of plasma. I've never heard of it being discussed as plasma, but
a hot gas. I mean, that's
could
sounds
be.
like the same thing.
I don't know. Yeah,
it's curious.
Yeah, they have achieved like tens of thousands of degrees with sonoluminescence tests, but it's a tiny amount. But yeah, it would at that temperature, it would be a plasma.
And then as soon as it expands, it's cold.
It's cold again. I mean, it lasts for fractions of a second.
So,
but it is plasma.
Okay. Randall, jump in here.
Yeah.
We wrapping it up? We're probably at the end of the show here.
Yeah, we probably are.
Yeah.
I have more questions than anything else about this now.
All of us do.
I mean,
but they're unformed. They're just vague. They're not even questions. They're just have question marks.
Question marks floating above you right now.
That's right.
I do too, man.
Well, this is good. This is a good sign, I would say. We need to be asking questions about this. So here's just a short diagram of the vortex tube, also known as the rank Hilsch vortex tube, a mechanical device that separates the compressed gas into hot and cold streams. The gas emerging from the hot end, which you'd see down, are you seeing my cursor?
Yeah.
Okay. Here, right, the hot end can reach temperatures of 200 degrees centigrade or 390 degrees Fahrenheit.
Does this work with concentric tubes, or just the one tube?
It can be one tube.
One tube. And so this is compressed air being introduced into the pipe here. Room temperature, ambient temperature, compressed air being pumped in here, and it creates this vortex, as you see here. And as this vortex moves down through the tube, it gets hotter and hotter, right? Until it can get to 390 degrees Fahrenheit, right? And the gas, and then this conical structure here is critical to the functioning of the thing, because somehow, and this is where I'm still trying to get my head wrapped around it, this cone at this end allows the escaping hot air, and then you see this, it flips and reverses the flow of the remaining air and sends it on another vortex down the inside of the first vortex, getting colder as it moves, and then it discharges from the other end, and the gas emerging, like it says here, from the cold end can reach 50 degrees centigrade or 60 degrees Fahrenheit. So you're looking at 390 plus 60 degrees. So you're looking at 450 degrees.
Yeah, I would suggest that this is somewhat like a centrifuge, because the hotter air is lighter. It's less dense. Right. The cold air is dense and it's spinning, so that the denser materials will move to the center. Right.
And so, and as far as the vortex tube, as I've been reading up on it and trying to learn about it, there is no consensus on exactly how it works, other than because there's no moving parts. The only thing moving is the air. So that's pretty wild. And
this is part of that Malcolm's system.
Well, part of the way the thunderstorm generator is the same principle. Now, these vortex tubes are used throughout industry. They're used in cooling of nuclear reactors. They're used in the air conditioning industry. They've got uses. They're being used by people who have no idea how they work or why they work.
That's great.
But they're still being used.
Yeah, it's really cool.
It is. Now, what Malcolm has done is he's got two concentric pipes, and the inner one is so the two vortexes are flowing, into two pipes. And then he's got spheres at the end. The spheres are the swirl chambers. Now, see, this is the swirl chamber. This square represents the swirl chamber. So it's the air comes in, and then somehow it sets up into this vortex. And I'm still trying to figure out how the hell that works, but that's basically the principle.
It could be a cylinder. It's a square.
It could be a sphere, and that's
cylinder.
That I think is the improvement and the innovation, is that he's got two sets of concentric spheres on either end of the tube. But he's also introduced the cones in order to create this effect, and then somehow that's why it's called a thunderstorm, because when you have a thunderstorm, you have a cold and a hot front meeting, and then as a result of that, it creates plasmas that then discharge in the form of lightning. So that's the principle of the thunderstorm generator. And, Jordan is at Alchemical Science is doing a really good job of trying to give some kind of rational explanation for what's going on. But now we're going to have hopefully hundreds of people, this, and that's the thing. This can be the kind of thing that somebody could actually build in the garage. The hardest part of this is the manufacturing of the spheres. But one of the things that George has gotten involved in is, and Mike Robertson, Mike Robertson and a friend of his who's a mechanical engineer and has a shop, they've built a thunderstorm generator according to the specifications. So they haven't done anything with it yet, but they've built it.
Well, if Malcolm's system works, then what he's done is save the internal combustion engine.
In effect, yes. That's exactly right, Mike. And he's basically changed the whole function of the internal combustion engine. And it completely you have to re-add water to the system periodically. But the only fossil fuel is used to get the initial ignition temperatures to generate the plasmas. And then once that's done, then it completely recycles everything, and all you have to do is add a few liters of water periodically.
Or you could add Gatorade. It's got electrolytes.
Well, that's an idea. Maybe. So anyway,
Gatorade in the bubbler is always best.
You never saw. Okay.
Yeah. All right.
Sorry. That's a movie reference, Randall.
Oh,
You never saw Idiocracy?
no, I didn't.
Oh no, you have to. All right.
Okay, I'll watch that, Russ.
It
If
was
you watch
It's
Fargo.
a bad joke.
No.
No to Fargo? You're not going to watch Fargo?
No way.
Russ has not figured out that it's a comedy. See, he sat down and started taking it seriously. He didn't realize it's a comedy.
It's a very dark comedy, but it's a comedy.
It's a comedy, yes. And the comedy, a big part of the comedy is the whole setup, and you don't get the setup in the first 10 minutes.
I didn't leave. I watched it for like an hour, and I was like, "This is the worst, most awful thing I've ever seen in my life."
My wife had the same reaction.
Maybe it was 45 minutes, but I sat as long as I could, and I was like, "Bro, I'm leaving." Leaving my popcorn here in the theater and walking out.
Yeah, but now, on the other hand, aren't you a fan of Big Lebowski?
Oh yeah, Lebowski was pretty funny. Yeah.
Yes.
Okay.
But at the same time, I was watching it, I'm like, what the hell am I looking at? But there were some funny parts, yeah.
Well, the first time I watched Big Lebowski, that was my response. Like, what?
Yeah.
It was like this. I've watched it, I think, 3 times now. And each time I've got, okay, I think I'm getting it now. I'm getting it. And that's his Fargo. You gotta
It's
give
absurdity.
it a chance.
It's absurdity. You know, the Coen brothers deal in absurdity.
Well, I might
have better things to do
resonate
with my time, guys.
with it. Oh, yeah?
Yeah.
Like
I do.
what?
I got a whole lot of video games to play.
Yeah, there we go. Yeah. Okay, now we're getting down to the
Pac-Man, bro. I'm still trying to beat Pac-Man. I'd rather do that than watch Fargo.
After 30 years,
Yeah.
you're still trying to beat Pac-Man. God, I haven't played a video game in so long. I know that they've gone completely, what they've got out there now compared to when.
Yeah,
I mean,
you need to play Far Cry Primal, bro. It's takes
really?
place in the Ice Age. You get to
Brad.
Yeah, Brad's like, we need to end the show. Yeah.
Well,
Okay.
we're getting a machine shop, so I'll hope to be building some of this stuff.
Are you
That'd be
really?
cool. Yeah, we just got an entire machine shop.
Oh, man.
Precision lathe
Oh,
and
excellent.
why I just name just went out of
CNC?
my head. No, a milling machine
Uh-huh.
and a bunch of other, parts of that metal
Either of
fabrication.
you guys weld?
Small precision
Yeah.
parts, yes.
Yeah, we can weld.
Okay. Well, yeah. You're going to you don't welding you need for the thunderstorm generator. You don't need it for the bubbler or the pre-ionizer, but you have to weld the pipes to the spheres.
Mhm.
Yeah.
That's the hard part. Now, there's talk about pre-making the spheres so that you could buy, and George Lush is in on that. He's got the annealing company that contracts out to the aerospace industry. And he's talking about developing a line of spheres using, advanced materials that they would be using, alloys that they would be using in the aerospace industry. But yeah, so I would say check out Gary Ling's site with those videos, and check out the which is ballsy thinking, strikefoundation.earth, and alchemical science. I can't remember Jordan's last name, but if you just put in your search engine alchemical science followed by Jordan, it'll take you right to the site. Or you can go to the YouTube where he's posting. I think he's got 5 or 6 video clips up now where he's methodically going through and taking stuff down, taking stuff apart, and explaining what he thinks is happening there. And then he's got it was sort of a collaborative effort between him and Nikita. So Nikita did the graphics, and he's put together a nice little presentation to do it yourself, how to build a thunderstorm generator and how to build the 3 components. Worth watching. Last thing I'll say, just remind people, if you want to help us out, the site Sacred Geometry International is still fraudulently selling my work and stealing not only from me and my family, but from the whole team here. And as we increase our fan base and our downloads and everything, he's using optimization techniques to siphon traffic away. And he's doing some really just crazy stuff on the site, conspiracy theory nonsense. And yeah, so you go there. I highly ask people to go to that site, Sacred Geometry International. And if you are so inclined, go to the social media and post that, and just let people know that anything sold, any contributions, none of it goes to me. None of it. I haven't seen a penny in over 4 years now from the sales of my work. Also, he's monetizing videos that Brad produced. So he's actually stealing from Brad. I think he's got some other stuff maybe that you guys have done. I know he's got some of Darren's stuff in his 90 video clips that he's got up.
He was selling access to like a big file with a bunch of podcast interviews you had done with other people's shows, and ours is in there. Brian Erica's in there, and a bunch of other people. So he's like selling our material.
Yes,
because it has you in it. Yeah,
and it's totally fraud, and people need to know. And I am gonna be putting something out so many people find out what's been going on. But if you want to help us out, let people know that site is completely fraudulent. He's been served with cease and desist, that he cannot use my name, my image, my work, but he continues to do it. So, it's really a toxic situation, and it needs to come to an end, and people could help with that just by spreading the word. Thanks.
Yeah.
So
RandallCarlson.com is the right website.
Thanks. Yep. RandallCarlson.com. You got it.
That's right.
Okay.
All right, guys. Wrap it up.
Back.
Yep.
Good night,
show.
Everyone. Hope you enjoyed the show. I think it was interesting.
Yeah.
Absolutely.
Good night.
Thanks, everybody.
Good night.
Good night, Mike.